Let's look at an introduction to inference for one variance. Here we'll investigate how to construct a confidence interval and carry out a hypothesis test for a population variance, if we are sampling from a normally distributed population. A note of caution right up front, these methods can work very poorly if the normality assumption is violated, so it's always a bit dubious using these procedures. Here's a quick example. The nutrition information for a major fast food chain claims that its deep-fried chicken sandwiches have 16 grams of fat. There is, of course, some variability in the amount of fat. Fast food chains strive for consistency, but they can't produce exactly the same product every single time. Maybe I'm alone in this, but I've wondered how much variability there is in variables like fat and calories and sugar content in fast food. A sample of 6 sandwiches from a large batch had a mean of 17.31 grams with a variance of 0.939 grams squared. On another day we might be interested in the mean, but today we'll discuss the variance. Here's the formula for the sample variance. It's a measure of how much dispersion there is in the data. The sample variance S squared is a point estimator of the population variance sigma squared. Sigma squared is the variance of the population from which we are sampling. When we draw the sample variance S squared will take on a value. In the example, S squared was 0.939, and this is a point estimate of sigma squared. But as we've discussed previously, reporting a point estimate is not usually enough. We want to use the data to say as much as we possibly can about the parameter sigma squared, and that includes reporting a measure of the uncertainty associated with our estimate. Here are some common points of interest when we are estimating a variance. We may wish to construct a confidence interval for the population variance sigma squared, or we might construct a confidence interval for the population standard deviation sigma. Or we may wish to test a hypothesis about the value of sigma squared, or the value of sigma. Here are the assumptions of the one-sample inference procedures for a variance. We need a simple random sample from the population of interest. If the sampling design is bad, then our results may be very misleading. And the population must be normally distributed. You may recall that inference procedures for means were robust to violations of the normality assumption, meaning they performed quite well for many violations of the normality assumption. But inference procedures for the variance are heavily reliant on the normality assumption. They can work very poorly when the normality assumption is violated, and large sample sizes do not save us from this problem. They work so poorly for violations of the normality assumption that we should be very wary of using these procedures at all. We've learned previously that the sample variance S squared is an unbiased estimator of the population variance sigma squared, meaning the expectation of S squared is equal to sigma squared. We don't need normality for that. That's true in general. But we do need normality for this second part. I discussed the sampling distribution of the sample variance in detail in another video. But for now, note that the sampling distribution of the sample variance is not normal. If we are sampling from a normally distributed population, then n-1 times S squared over sigma squared is a random variable that has a chi-square distribution with n-1 degrees of freedom. This is the Greek letter chi, in case you haven't seen that before. We are going to base our inference procedures for sigma squared on the chi-square distribution. A consequence of this is that confidence intervals for variances are created in a slightly different way than confidence intervals for means. If we are sampling from a normally distributed population, then a 1 minus alpha times 100% confidence interval for sigma squared is given by this interval. We'll usually use a confidence level like 95% or 99%. We find chi-square sub alpha over 2 and chi-square sub 1 minus alpha over 2 from the chi-square distribution with n-1 degrees of freedom. Here's a chi-square distribution. The mean and variance and shape of the chi-square distribution depend on the degrees of freedom, but this is a chi-square distribution. It typically looks a little like this, with some right skewness. The amount of the skewness depends on the degrees of freedom. If we want a confidence level of 1 minus alpha, We put 1 minus alpha in the middle, and we split up the remaining bit, alpha, evenly into the two tails. Chi-square sub alpha over 2 is the chi-square value that has an area to the right of alpha over 2, and we'll find that in the right tail of the distribution. Chi-square sub 1 minus alpha over 2 is the chi-square value that has an area to the right of 1 minus alpha over 2, which means the area to the left is alpha over 2. It would be in the left tail of the distribution. We will find these values using software or a chi-square table. We may wish to use a hypothesis test to help answer the question, is there strong evidence that the population variance differs from a hypothesized value? We may wish to test the null hypothesis that sigma squared equals sigma naught squared, where sigma naught squared is some hypothesized value that is of interest to us. We may also phrase this in terms of the standard deviation, that the population standard deviation sigma equals sigma naught. The alternative hypothesis will be one of these three options. The appropriate choice of alternative hypothesis depends on the problem at hand. To test that null hypothesis, we will use this chi-square test statistic, n-1 times the sample variance s squared divided by the hypothesized variance. If this null hypothesis is true, and sigma squared equals sigma naught squared, and the normality assumption is true, this test statistic will have the chi-square distribution with n-1 degrees of freedom. So we will get the p-value of the test from the chi-square distribution. Let's look at how we'll do that. Suppose we are using this alternative hypothesis, that sigma squared is greater than the hypothesized value. Here's the test statistic. And if the null hypothesis is true, the test statistic would have the chi-square distribution with n-1 degrees of freedom. I've drawn in a chi-square distribution here. Suppose we go ahead, draw a sample from the population, and calculate the observed value of the test statistic. We would draw it in on this distribution. I'm letting this chi-square with a subscript of OBS or OBS represent the observed value of the chi-square test statistic. If this alternative hypothesis is true, and sigma squared is greater than the hypothesized value, then the sample variance s squared will have a tendency to be greater than the hypothesized value, and the test statistic will tend to be large. So here, large values of the test statistic give evidence against the null hypothesis and in favor of this alternative hypothesis. The p-value is the probability, under the null hypothesis, of getting the observed value of the test statistic or something even greater. And that's simply this area, the area to the right of the observed value of the test statistic under the chi-square distribution with n-1 degrees of freedom. We typically find that area using software, but we could also use a chi-square table to find an approximate value. Suppose instead we had this alternative hypothesis, that sigma squared is less than the hypothesized value, but we had the same observed value of the chi-square test statistic. If this alternative hypothesis is true, and sigma squared is in fact less than the hypothesized value, then s squared will have a tendency to be less than the hypothesized value, sigma naught squared, and this test statistic will tend to be small. Here, small values of the test statistic give evidence against the null hypothesis and in favor of this alternative hypothesis. So the p-value is the probability, under the null hypothesis, of getting this observed value of the test statistic or something less, something farther to the left. And that's simply this area, the area to the left of the observed value of the test statistic under the chi-square distribution with n-1 degrees of freedom. Suppose the alternative hypothesis is changed to the two-sided alternative that sigma squared is different from the hypothesized value. Here, values of the test statistic far out in the right tail, or values of the test statistic far out in the left tail, closer to 0, give evidence against the null hypothesis and in favor of this alternative. The p-value is the probability, under the null hypothesis, of getting the observed value of the test statistic or something more extreme, something farther out in the tails. We're going to do something very similar to what we did in t-tests for the mean. We take the area to the left of the observed value of the test statistic, or the area to the right of the observed value of the test statistic, whichever is smaller, and double it. Once we have the p-value, we will draw a conclusion in the usual ways. A very small p-value gives very strong evidence against the null hypothesis and in favor of the alternative hypothesis. And if we are carrying out the test at a set significance level alpha, we can reject the null hypothesis in favor of the alternative hypothesis if the p-value is less than or equal to alpha. We could also say that the evidence against the null hypothesis is statistically significant if the p-value is less than or equal to alpha. I worked through a complete example in another video, but let's take a quick look at the results of these procedures for the example I introduced at the start. This S-squared value of 0.939 is the sample variance of fat content for 6 deep-fried chicken sandwiches sampled from a large batch of sandwiches. We might want a 95% confidence interval for sigma squared, the true variance of the fat content of chicken sandwiches from this large batch. If we worked through the calculations, we'd see that the 95% confidence interval for sigma squared is 0.366 to 5.648. We can be 95% confident that the population variance lies somewhere in this interval. Note that the sample variance does not fall in the middle of the interval. The sample variance of 0.939 is closer to the lower bound of the interval than to the upper bound. This effect is more exaggerated for smaller sample sizes. For large sample sizes, the sample variance will fall close to the middle of the interval. If we wanted a 95% confidence interval for sigma, the population standard deviation, we would simply take the square roots of the endpoints of the interval for the variance. So now we have some idea of the variability of the fat content in this type of chicken sandwich. This was an estimation problem, and there wasn't a natural hypothesis that we wished to test. So we'd typically be finished with our analysis at this point. But for illustrative purposes, suppose it was previously claimed that the variance in fat content is 1 gram squared, and suppose we wish to put this claim to the test by testing these hypotheses. Before we even carry out the test, we should have a pretty good idea of what the end result will be, because of the relationship between hypothesis tests and confidence intervals. If the hypothesized value is 1, this interval tells us that that is a plausible value of sigma squared. And the sample variance is quite close to 1, so we have a pretty good idea before we even carry out the test that there won't be a lot of evidence against the null hypothesis. You can verify for yourself that if we use the methods of this video, we'd get a chi-square test statistic of 4.695, and a resulting two-sided p-value of 0.91. This is a very large p-value, and so there isn't any evidence against the null hypothesis. There is no evidence that the true variance differs from 1. In another video, I worked through a complete example of these inference methods, including the full calculations.